ladies and gentlemen. Today we'll be embarking on a journey into the fascinating realm of big O notation. While this topic might sound like a daunting venture, I promise to be a friendly guide through the dense forest of computational efficiency. The language of efficiency. Imagine you're planning a road trip. What's the first thing you consider? Well, it's usually the estimated time it will take to reach your destination. Similarly, in the world of programming, we are often concerned with how long our algorithms will take to complete. That's where big O notation comes in. Big O notation is a way of describing your efficiency of an algorithm. It's like having a universal language to discuss how our code performs. Instead of saying this algorithm is faster than that one, we can say the time complexity of this algorithm is big O of n, while the other is big O of n squared. Meet the notation. Now let's get to know the stars of our show, the big O notations. We have big O of 1, big O of log n, and so on. Each one tells us something about how an algorithm scales with input size. Big O of 1. This is like magic. It means that your algorithm takes the same amount of time regardless of how much data you throw at it. Think of it as a dictionary lookup. It's almost instant. Next up, big O of log n. Logarithmic time is efficient. Imagine you're looking up a name in a phone book. As the book gets thicker, the time to find a name doesn't increase proportionately. It's quicker than linear time. Big O of n. Linear time is like going through a to-do list one item at a time. If you have 100 tasks, it will take about 100 times longer than having just one task. Big O of n log n. This is often associated with efficient sorting algorithms like quicksort. It's faster than quadratic time, but not as magical as big O of log n. Big O of n squared. Quadratic time is like comparing each item in a list with every other item. If you have 100 items, you need to make 10,000 comparisons. It's not very efficient. You get the idea. Big O notation is our compass for understanding the scalability of algorithms. Taming the beast. Alright, let's tackle some classic data structures and their big O complexities. We'll start with arrays. They are simple but powerful. Accessing an element by index is big O of 1, which is great. But inserting or deleting an element at the beginning is big O of n, not so great. The same goes for linked lists, which shine when it comes to inserting or deleting elements, but not so much for quick lookups. Now let's talk about the dynamic duo, stacks and queues. Stacks follow the last in first out principle, while queues follow first in first out. Both are efficient for adding and removing items, but lookup time is big O of n because you have to search from the beginning. Trees are like the Swiss Army knives of data structures. The binary search tree is particularly nifty. On average, searching for a value is big O of log n, but in the worst case, it can degrade to big O of n if the tree becomes unbalanced. Hash tables, though, are superheroes when it comes to quick lookups. On average, they are big O of 1, but beware, in rare cases, collisions can slow them down to big O of n. The quest for efficiency. In the realm of algorithms, we are always on a quest for efficiency. Quicksort and merge sort are like gallant knights who sort arrays quickly, typically in big O of n log n time. Then there's the formidable knight bubble sort, which sorts with a time complexity of big O of n squared, and is quite the workhorse. Searching algorithms are like treasure hunters. Binary search, a star among them, is often big O of log n, while linear search is big O of n. It's all about choosing the right tool for the job. Practical applications. Big O notation isn't just theory, it has practical applications. Think about databases. When designing a database, we aim for efficient queries. We want to retrieve information quickly. The choice of data structures and algorithms can make a significant impact. In web development, we optimize code to ensure web pages load fast. Big O notation helps us analyze the performance of different solutions. Real-world examples. Now let's look at some of the real-world examples. You are building a social media platform. How do you ensure that your timeline loads quickly even if a user follows thousands of people? Big O notation helps you choose the right algorithms for managing the feed efficiently. Or consider a GPS app. It must find the fastest route from point A to point B. To do that, it employs efficient graph algorithms that ensure a speedy arrival at your destination. In conclusion, Big O notation is our trusty guide through the wilderness of computational efficiency. It's the language we use to discuss and evaluate the performance of algorithms and data structures. By understanding the Big O notation, we can make informed choices to build efficient software, making our digital world a smoother, faster, and more delightful place. Thank you for joining me on this journey, and remember, whether you're coding for fun or any other purposes, knowing Big O notation will be your invaluable companion. Happy coding!